All right. We are already recording. Welcome to another seminar of the Commission G5 of the IAU. We are recording the talk and will be stored at the IACTalks website with all of the talks from this series. Good afternoon, everyone. Today we count on Andreas Sander from the University of Heidelberg, from the Instituto in Germany. Andreas was graduated in physics at the University of Potsdam, where he also got his PhD in astrophysics. He was a postdoc at Armagh Observatory in Northern Ireland, and now is the another research group leader at ARI. And his work revolves mainly around the stellar atmospheres of massive stars, and that's precisely what he's going to give us today, an update. The title of the talk is Understanding the Properties and Impact of Hot Massive Stars with Detailed Atmospheric Modeling. Please keep your microphones off and cameras off, and at the end we'll have some time for questions and comments. Andreas, welcome.
Thank you very much, Carlos, for this very nice introduction. Yeah, so I don't really have to introduce myself anymore and can stump right away. I see that we have quite a mixed audience, so some of you will know a lot of what I'm talking in this talk. Others might be further away from the field. So I'm trying to give a broad overview for all of you. So yeah, my talk is called about understanding the properties and impact of hot massive stars with detailed stellar atmosphere models. And I'm not doing that alone. I'm doing this together with my research group that I started in 2021. So a bit more than 3 years ago at the ARI in Heidelberg. But first, let's define a bit here in this context what we actually mean with massive stars, or what I mean with massive stars when I talk about it. So massive stars sometimes are already defined for stars larger than 3 solar masses, but in the context of this talk here, this would be more intermediate mass stars. While the typical limit that I will set here is really the 8 to 10 solar masses. It depends a bit on whether you take carbon ignition already as the limit, or really if you want to go all the way with neon ignition. So stars that eventually undergo core collapse, that's how what I would define as massive stars in the context of this talk. Of course, these stars have much shorter lifetimes. They have the higher mass leads to a stronger gravitational force. The core temperature is much higher, so the nuclear burning time scales are lower. And these stars are typically also very luminous, and the 20,000 that I list here on this slide is really a lower limit. Most of the stars that you will see in the HR diagrams in the following slides are really much more luminous than that. And then one of the main goals that we're really trying to understand is how do massive stars evolve? Because what you see here in the background as an image is you see a young region of OB stars in the upper right corner, and then you see, for example, a Wolf-Rayet star in the lower left corner, and we really don't have a good clue on how these stars evolve. Yes, you will find something in the literature. You will also see it 2 slides ahead, but how this really happens in detail and what happens for particular parameter regimes is still quite uncertain. So massive stars really have a fundamental role in astrophysics. In the more recent years, we can often start with the detection of gravitational waves, which come from merging black holes, which then are the endpoints of massive star evolution together with neutron stars. But massive stars really interact with their environment early on. They can ionize their surrounding. They can lose mass intrinsically or via interaction with their companions. So this is what is called stellar feedback. And of course, this then influences further stellar evolution. It has an important role for the origin of elements. It can set the stage for new star and planet formation. And the ionizing flux of earlier massive stars is even a crucial ingredient in understanding cosmic reionization. So all in all, massive stars really have this key position in a complex network of astrophysics, and this is why it's quite important to understand them. Now, for most of their evolutionary lifetime, massive stars are actually in a hot stage, meaning that the effective temperature is hotter than around about 10 kilokelvin. But what you see here in this example HRD on the left side, which is for a selection of massive stars in the LMC, is that there's actually quite a zoo of different objects that are massive. Of course, there are also cool massive stars like the red supergiants and the yellow supergiants indicated here, but you can already see the bulk of the main sequence, and then a lot of stuff around it is quite hot. And so their flux maximum is in the UV, which makes them interesting ionizing sources, and they come in various spectral types, from B stars, O stars, over various flavors of Wolf-Rayet stars. And as I mentioned initially, there's lots of open questions. I might not need to talk about this in detail here, but you see already that these tracks that we just plot there, for example, they go into a regime where there are no observed massive stars. On the other hand, there are stars where none of these tracks connect to. So we already see that this simple picture of standard single star evolution alone with certain fixed ingredients really doesn't explain the population that we see, for example, here. And the only way to make progress in that is to really study the different observed zoo members, and in order to really figure out what's up with them and how we can properly connect them. So to make some motivations on why this has something to do with stellar atmospheres, it's really a danger if one would just guesstimate stars, right? So photometry is nice, but alone it's usually insufficient for hot stars, because especially once you get hotter than about 20 kilokelvin, you can essentially fit almost any model if you just slightly adjust your reddening. It's blue. From the optical colors that you typically get with photometry, you cannot distill the temperature anymore alone. Also, if you use spectral types in the literature, that's quite dangerous, because many literature values are from older low-resolution spectroscopy. So you will very often have undetected binaries, and even if you get some spectral type, that doesn't automatically tell you the evolutionary status. Yes, of course, if you have a dwarf star, you will usually interpret it as an unevolved main sequence stars. But as we see here, for example, with two different recent examples, this can be quite different once you start analyzing the system in detail. So here are these two examples. The first one, which was originally classified as an early O dwarf, and from this you would infer that this is a very massive, or not very massive formally, but a high mass star of more than 60 solar masses. But once we made the effort to look into the system in more detail, you see that it actually is a binary system of two stars that have interacted, and even if you add their masses together, you don't reach the mass that would just be inferred from their older spectral type. And the second one is a slightly different example for a partially stripped star, but I will come to that later during this talk. So how to deal with hot massive stars? Well, I guess you know the answer, since this is the G5 Commission. You need to perform quantitative spectroscopy with proper stellar atmosphere models to get reliable parameters, and then only afterwards compare them with evolution models, and avoid using any assumptions from the evolution track already in your analysis, because this is often where you can tend to make incorrect assumptions, and then this propagates into the inferred stellar parameters, which we want to avoid, in particular in this hot massive star regime. So for quantitative spectroscopy of hot massive stars, it's important that we usually cannot use a decomposition into element-specific models. So we really need to calculate already the stratification with the whole set of elements that we later want to have in the spectrum. And so we have one model to explain all of this, what I plot here, namely an observed normalized spectrum, and then if you are lucky, you might have HST flux calibrated spectra and a range of photometry that really tell you everything about the object that you want to study. This requires a lot of different things, and I'll come to that in a minute. But for a second, let me just also tell you a bit about the diagnostics that we use. So for most stars, we cannot just, as I said, infer the temperature from photometry. So we need to look at the actual spectral appearance. We need to look at the different spectral lines, and then we can compare, for example, line ratios such as helium-1 versus helium-2. And then depending on which regime you are, you also need to take further lines into account. For example, these nitrogen lines here for early O stars are very important, because at some point you lose the helium-1 diagnostics. Or for B stars, you want to have the silicon lines in order to determine the temperatures. And together with all of this, we usually need to determine a whole selection of further quantities. We need to know the rotational broadening, which we like to use metal lines. We need to determine the microturbulence, the macroturbulence, and of course wind and clumping diagnostics. Now, The physical roots of quantitative spectroscopy are, of course, going back to our assumptions about stars. So stars are giant balls of gas, which means they don't really have a hard boundary. So we define their radius typically via an optical depth or a Rosselin optical depth. And the spectrum that we see stems from this transition layer that we call the stellar atmosphere, which modeling is really a fundamental tool of astrophysics. For hot stars, this is particularly challenging because the spectrum formation is far outside of thermodynamic equilibrium, and the stellar winds are also altering the spectrum and need to be modeled. So we also need to think about what to do. We need to calculate a so-called expanding atmosphere models. In this atmosphere, we can have ionization changes which need to be taken into account. And we also have multiple broadening mechanisms for the emission and absorption lines. And that means that in total, we really have a significant set of physical and numerical challenges. Now, without going into detail for all of them, I've listed them here very briefly. We have the non-LTE situation, so we need to do a detailed statistical equilibrium. We need to account for the fact that photons will scatter, or can at least scatter multiple times before actually leaving the interesting part of the stellar wind. And we have to account for the expansion. I mentioned that already, but this also means that we have to connect the essentially hydrostatic layers where the absorption lines are forming to a highly supersonic wind regime. We then have to think about if one can still define a certain temperature, which is possible for the electrons in the system, and to get a proper temperature stratification. And last but not least, all these different elements can quite influence our stratification. In particular, interesting there are the iron or the group of iron elements, because you have so many levels and so many transitions between them that they act like a blanket sitting on the star and considerably change, for example, the temperature stratification. And this, of course, cannot be calculated explicitly anymore. We are speaking about millions of transitions there, and so you need to do something that's called super levels, which you then can use to treat this regime. So going a bit more into detail for some of the fundamental parts, that's the calculation of the non-LTE regime, which in contrast to cool stars is here not just in the final step where you calculate the spectrum, but also during the main iteration, because the departures are typically much larger in hot stars from LTE than they are in cool star atmospheres, which means the non-LTE is not a correction, but it's really the inherent treatment of the atmosphere. That means also that we need an iterative solution for the statistical equilibrium equations. Modern models usually have around 1,000, 2,000, maybe a bit more explicit levels. And in particular, abundance changes in one element can affect lines of other elements. That's not necessarily true for all elements, especially the ones with low abundances, but I just talked about iron. So if you include or not include iron in your model will have a significant effect, and we cannot calculate realistic hot star models, for example, without considering iron already during the iteration. Then hot stars are, stellar winds are ubiquitous in hot massive stars. They will alter the spectrum, in particular if the wind strength is not negligible. So this needs to be modeled in this expanding framework. And in hot stars, in particular, radiation pressure dominates. You still need to think about gas pressure, but radiation pressure is typically dominating over gas pressure. And so what actually drives the wind is, beside the three electrons, a momentum transfer from the photons to the matter in the absorption of spectral lines. And because the radiation is mainly coming from the radial direction and the re-emission will be in an arbitrary direction, you have this radial net outflow that pushes out your outermost layers. Now, people realized early on in the field that this is subject to instabilities, but there is the existence of time-averaged stationary solutions. And if you write that down, for example, here, the radiative acceleration versus gravity in 1D, you get this balance of quantities with fundamental quantities L and M, and that kind of makes sense, right? You have more luminosity, so you can drive a stronger wind, or you have a star of a higher mass, which means the gravity that tries to pull the matter back is getting stronger. And then you have this harmlessly looking quantity here, which is called kappa F, which is the flux-weighted mean opacity. And this is one of the reasons why we need detailed modeling, because this harmlessly looking quantity is all but actually harmless, because if you try to calculate that and compare it, for example, with tabulated Rosselin opacities, you will discover that in the outer wind path, so where it's getting interesting in terms of the stellar wind and also the effect to the spectrum, you have a significant difference of the flux-weighted mean opacity, which is considerably higher than tabulated Rosselin opacities. And the reason why this opacity is so much higher is that your lines can be Doppler shifted because they are the layers are accelerated, so your lines are shifted due to the Doppler effect, and they are exposed to fresh flux, which can then again accelerate the line further. So instead of what I'm sketching here, instead of having just a small Gaussian profile where you could absorb the line, you actually shift this over a wide wavelength range and thereby significantly extend the amount of flux that you can absorb, which is then used to drive your stellar wind. Now, in order to treat that in an expanding framework, what we do is that what we do in our code that we work in our group with is that we do a co-moving frame radiative transfer calculation. This is, bluntly speaking, a brute force numerical solution of the spherical radiative transfer equation with a basic concept going back to Dimitri Mihallas in the 70s, but with various later extensions in order to handle the current problems. The advantage of doing this in the co-moving frame is that your opacities and emissivities stay isotropic despite the expanding atmospheres, but you buy this at a significant numerical cost. So you typically have in these models between 200 and 400,000 wavelength points, depending on the required line width solution. And you also have an initial value problem. So you need to start your solution at the blue edge and then solve for each wavelength point while using the solution for the last wavelength point. And already at that moment you see that this is not a good task for parallelization, so this is why this is computationally expensive and we actually need significant single CPU power in order to make that feasible on a reasonable time scale. And then at each wavelength point you have an equation system that's coupled in space. So in total, if you solve that in the typical PZ geometry, you have about 10 to the 9 intensities. This is quite numerical costly, so the global scheme is then trying to reduce this numerical effort a bit and doing this ray by ray solution only every few iterations, but instead calculate the angle integrated moments from that, define so-called Eddington factors as closure relations for the moment equations, and then solve only the moment equations for a typical number of 6 iterations, which reduces our calculations by 1 dimension, which is quite significant in terms of gaining speed. The benefit of doing this CMF radiative transfer calculation is that you implicitly include various effects that you otherwise don't account for if you try simple approaches that are faster, for example, multiple scattering and also the overlapping of the lines. And you also don't need the so-called Sobolev approximation, which gives you a much better line force, at least in critical regimes where the Sobolev approximations would otherwise break down. But as mentioned, each of these computations with detailed atomic data takes a few minutes, and that means if you iterate over this, atmosphere codes using this approach will require hours to days in order to converge a model. And as I just mentioned, you need this iteration, so all of this stuff you don't have to do just once. So you iterate between the radiative transfer and the rate equation, so symbolically written as the radiation field uses an operator lambda working on the source function that includes the population numbers, and then in turn you need to calculate the population numbers via solving this high-dimensional system of equation with a almost block diagonal matrix P, and this P is a transition rate matrix including for radiative and collisional transitions, and of course in the radiative transitions you have the radiation field back, so you have a high-dimensional nonlinear system fully coupled in space and frequency. But you can set up this machinery, and then this machinery basically uses the stellar and wind parameters, and then it iteratively corrects for the temperature stratification. It solves the equations for statistical equilibrium, and it uses the CMF radiative transfer. And once each of these steps doesn't cause a major update in the other steps anymore, we consider our model converged and then transform into the observer's frame in order to calculate the emergent spectrum. And this you can then compare to an observation like the one here in the lower left, but you can also use these models obviously to infer stuff that you cannot observe easily. For example, the ionizing fluxes beyond the Lyman edge. And here is just an example model where I color-coded the flux beyond the different ionization edges for hydrogen, helium-1 and helium-2. And this is important, for example, to infer the ionizing feedback of the stars. Now, the code that I'm using is not the only one. There are a few codes that are used in our field. If you have a negligible wind, you can get away with using a plane parallel code. The typical one here is JWST, which includes proper iron line blanketing. And then if you need to use an expanding code, there are essentially three that are used in the field of hot massive stars: fast wind, CMF, gen, and power. The one that I'm working with is power, which I've used here in this HD variant, and I will come back to in a minute while we're doing that. So with these models, you can basically analyze hot stars across the different regimes that we have. So OB dwarfs, giants, supergiants. You can use that for Wolf-Rayet stars, which I'm showing here in the uppermost panel. The lowermost panel shows a low metallicity O star. Of course, you can also combine models in order to understand multiple systems. Here is, for example, a Wolf-Rayet star that has actually even three OB star companions, and then you can try, if you have multi-epoch data and maybe some additional photometry, you can really spend some time, but you can find solutions where you explain all of the different components to the system and then try to disentangle that. Yeah, binary strip stars, LBV candidates, very massive stars. You can even go to the low mass regime as long as you are staying on the hot side, because we don't do molecules in this code. So you can analyze, for example, hot central stars of planetary nebulae. There are some limitations, but ask me about that if you want to know more. Because we're doing more than just spectral fits, but this detailed physical model, we can we enable with these calculations also environmental predictions, as I mentioned already, feedback, but you can also see if the surrounding is, for example, reasonable enough for dust formation, for example. So now let me go through some of the efforts that I'm doing or have recently done in the group. I've made some selections, and this is by far not all, but of course I had to make some choices given the amount of time. So for example, my postdoc Varsha Ramachandran has worked on high mass X-ray binaries. 2 years ago published a paper on the exemplary analysis of M33X7, where you have an O star with a black hole. And in this case, you have a particularly interesting situation that the stellar wind is not the same depending on the orbital phase, because you have the black hole accreting, which generates X-rays, and then the X-rays again are disturbing the stellar atmosphere. And we had, this is still a spherical model, so it's not a perfect approach, but within these limitations, we can try to account for the X-rays and then model this time-dependent change of the UV spectrum where we had phase-resolved UV spectrum. And currently, actually, Varsha is working on another high-mass X-ray binary, namely the famous Cygnus X1, which interestingly has only been analyzed with JWST from the modern model atmospheres, and we are now doing the first expanding model atmosphere codes, at least as far as I'm aware of. More recently, Varsha has published something on stripped stars, so I also wanted to talk about that. So there are many products of binary evolution. I told you in the beginning that this whole system of how stars evolve from this OB star stage to more evolved stages is quite uncertain. And binary evolution predicts a lot of interesting systems that at least a few years ago were basically not yet observed. So there was a lot of discussion, or there still is a lot of discussion, about binary interaction products that are more or less hidden. And hidden often just means that, yes, sometimes they are outshined, but in other cases, somebody just didn't look carefully enough with, for example, multi-epoch data and high-resolution data at the system in order to find the signatures that instead of one star, you're just seeing two. And so we could do that, for example, in the Ulysses and XShoot framework, which is a big effort to have optical and UV data for prototypical or hopefully prototypical massive stars in the Magellanic Clouds. And there, Varsha looked for suspicious signatures in the spectrum. And one of the suspicious signatures I'm showing here on the right hand side. So what you see there is the silicon doublet, and as you see 4 lines, you already notice that maybe this is not a silicon quartet, that's what your atomic data will tell you, but it's actually 2 times the silicon doublet. So instead of 1 star, you see 2 stars here, and signatures like that then help you to identify also the winds of both of these stars, because these stars here in the UV are actually heavily influenced by the wind and allow you to constrain the winds of these stars better. So we published this in a paper earlier this year in this X-shooting Ulysses series, where 3 new partially stripped stars were discovered. There has been an earlier discovery in the SMC, and because we have the UV spectra here, we really have mass loss rate determinations, and Varsha could show that the mass loss rates of these 2 stars here in the LMC, for example, exceed the typical mass loss rates of O stars, but are not as high as the mass loss rate you would expect it from Wolf-Rayet stars, which are more seen as the classic result of binary stripping, because you have a strong winded star that's easy to detect even in stellar populations. We're also trying to go a bit to even lower metallicity. We have some stars in the Magellanic Bridge, which is this region between the LMC and the SMC. And the interesting thing is that we had indications from the optical here, also from an earlier work by Varsha, that there are O stars in the Magellanic Bridge, which wasn't known until 2020. And at least some of them have quite a low oxygen abundance, and so we took HST spectra for them, and we now see in the work that Elisa Schösser is doing, a PhD student of mine, that indeed these low metallicity O stars also contain a quite low iron abundance, and we're hoping to submit that very, very soon. Now, I talked about the different codes that are there for stellar atmospheres, and of course, especially in the framework of this X-shoot-U collaboration, we were also interested to learn, like, what do we actually need to do when we compare different sources, right? So how much do the results really differ if you use, for example, the power code, or if you use the CMF-Gen code? And for doing that, we met about 2 years ago now and decided, let's do a blind test. We want to avoid any aims in order to meet expected values. So everybody does what they're doing. Don't tell your values up front to the others, but use the stuff you usually do. So for example, if you want to renormalize your spectrum, then do that. Yeah. But we wanted to use the same photometry at least, and the same source for the spectrum. So not that somebody takes a different time spectrum from a different date or something. In the end, we had 3 different codes employed and 8 different methods, reaching from coarse grid to tailored models. The results from the paper is that the typical spread one would get is around 3000 Kelvin, and a difference in log G by up to 0.2, with a difference in the luminosities by about 0.15 dex, which is a bit more than we expected, because especially if you then go to the mass loss rates, this is about a factor of 0.4. So this is even more than a factor of 2. The main reason for this is actually not so much the codes, but the different reddening approaches and the different assumptions for the clumping in the wind. So we would like to do a follow-up study in order to break that a bit more down if you use the same reddening. That's currently something that we are discussing. The turbulent pressure, what we figured out there, is also one promising thing to reduce the so-called mass discrepancy, because typically there, or not typically, but quite regularly we find a mismatch between the mass that you derive from the spectral analysis and what you would do if you just use a stellar evolution track and then from the HRD position try to infer the masses. But the good news here is it's usually okay to combine results from different models. You just need to be aware that there will be some typical spreads that also could go beyond the typically reported error margin from the individual models. Now, the stuff I've talked so far is the more standard way of using quantitative spectral analysis with empirical stellar and wind parameters, but formally they are both independent parameters of the model. And if you think about this from a physical perspective, this actually does not need to be, because the wind of a star should follow from its fundamental parameters if you know the physics that are involved in driving the wind. So what about constructing a unified model for the star and the wind and having consistent parameters? You can do that, but it comes at again at a numerical cost. You need to change this scheme to a scheme where you include the hydrodynamics, at least in a stationary approach. And as you can see from the increasing numbers of arrows, you have a significant addition of dependencies, which makes this also a bit more cumbersome to calculate. But in principle, it's possible, and you just take away the wind stratification here from this input part and put it as part of the corrections. Which is why I added this HD here to the power logo, because it includes the hydrodynamics. And with this, you can, in principle, if you have all the necessary elements driving your wind and you have a radiation plus maybe gas pressure driven wind, you can predict the mass loss rates and also the wind velocity field. Now, this basically turns your stellar atmosphere model also into a theoretical laboratory. So in principle, you can now use the details and the numerically costly radiative transfer, turn that into an advantage and say, okay, if I have to include all of these ingredients, I can also figure out how all of these different ingredients contribute to the radiative acceleration of a stellar wind. And this is shown here with this logarithmic scale for the radius. So on the left, you see the inside of the photosphere, and then in the outer part right, you see the outer part of the wind. And this is a logarithmic scale normalized by gravity, just to make it easier to plot. And you basically see that in the inner part, you have here also the free electrons, which contribute significantly, but on a basically constant level. And then in order to get beyond that, you need the contributions from iron. And then in the outer wind, you have a plethora of different ions that boost your radiative acceleration, and that will also help you to determine your terminal velocity. This looks like this for a zeta Pappes-like model with 41 kilokelvin, but actually if you do models in different regimes, you will see that the the lines change, and also the colors change, and have used the same colors for the same ions. So you see when you go to different regimes, the contributions to the radiative acceleration change, but usually the iron opacities will still play the key role for launching your winds, which means that the mass loss rates are significantly depending on the initial metallicity. All right, now I've talked a lot about the models. Let's talk one of the main applications on why I used this model in the past and what we're still doing in the group, namely the winds of Wolf-Rayet stars. If you take a spectrum of a Wolf-Rayet star, you will see this emission line dominated spectra, at least for the typical Wolf-Rayet star. And actually Wolf-Rayet stars are a spectroscopic definition. They are defined by something that essentially looks like this, right? So that indicates a strong mass outflow, and we have two different types of stars that fulfill that. If we forget about low mass Wolf-Rayet stars for a moment, namely the classical ones, which are defined as core helium burning evolved stars that have partially or completely lost their outer hydrogen layers. And then we have very massive stars, which are core hydrogen burning stars, so barely evolved, and are essentially an extension of the main sequence, which is why they are sometimes called O stars on steroids in our business. Now, these models that I just explained to you, the hydrodynamically consistent models, you can use them to study radiative wind driving for Wolf-Rayet stars, which has remained quite enigmatic for a while. There have been some pioneering efforts by Götz Gräfner about now almost 2 decades ago, demonstrating that it's the iron M shell that launches this wind, but you needed a significant number of these models in order to find any trends. So what we see already here is we have now a double bump structure compared to the plots that you saw earlier, where you have just a single peak or a single trend in this. And it's really this inner hot iron bump that we call, which is iron 9 to iron about 14, that already launches the wind of these stars. And then you have a strongly non-monotonic behavior of this flux-weighted opacity. And this is actually the reasons why simpler descriptions for the driving of stellar winds have failed. So here on this plot on the upper right, I plotted the so-called force multiplier, which you can define in the framework of the CAK parameterization that is typically used for OB stars. And you can see that if you define that as a function of this optical depth parameter T, then what you get for a dense wind is something that's not describable as a function anymore. And that's one of the reasons why this breaks down when you want to describe Wolf-Rayet stars, because here is, for example, a B supergiant, you have this single bump structure, but here for the Wolf-Rayet you have this double bump, and this no longer allows to use this T-like optical depth variant. Now, if you run hydrodynamically consistent models for a large set of parameters, you can use that to infer, for example, here mass loss recipes. So this is what I did together with Yorick in the 2020 paper, where I created a large set of models, in this case for WN-type Wolf-Rayet stars, and varied the masses, but also the metallicities, and then you can plot them in different coordinates and try to find a regime that's not just doing some least square fit, but that's really trying to map as good as possible the shape of what you get from these models. And this led to a new Wolf-Rayet mass loss recipe that since then we have tried to improve a bit further, because this is just for one set of temperatures. If you also include the radius dimension, you then get an additional effect that you needed to account for example, here in this m dot times the critical radius to the power third scaling. So you can significantly describe the mass loss rate based on the fundamental stellar parameters. There are still further dimensions that we would like to add to this regime, but it already has shown something that was not known so far before, namely that this typical Wolf-Rayet mass loss breaks down very abruptly below a certain limit that is highly metallicity dependent. And that was quite interesting, because that fitted relatively nicely with the disappearance of Wolf-Rayet stars below a certain luminosity regime. So I won't bore you here with the details, but essentially now in the group we are using this machinery to also go to different parameters and to also benchmark what we find in the atmosphere models with other observations. So one example is here, that's work from my PhD student Roel Lefevre, who is trying to analyze the well-known Wolf-Rayet binary WR140. That's the one that yield this famous JWST pictures here now about 2 years ago. And we're using this because we can then compare the masses that we need, for example, for our model with the orbital masses that are known to in the system. And we also see that we require a very, very thick wind model that is basically reaching further out than what we typically would use. Maybe 1,000 or even 10,000 stellar radii are not enough here. We really need to go to 100,000 stellar radii, which is quite numerically challenging. We can also do that then to employ it for stars where we have no chance to ever get orbital masses. So for example, here is another work from Roel in the galactic center for a star that's called LHO99. And we can determine that this star is indeed already evolved. It only has 45% of surface hydrogen left, but it's also quite massive with about 75 solar masses, current mass. We are trying something not too dissimilar also with B hypergiants. So that's another paper by my student Matthäus Bernini-Perron, currently in the work where he's analyzing or finding a model that resembles, this is the more precise way to phrase it, the B hypergiant Zeta 1 SCO, which needs a current mass of about 35 solar masses and about 55% surface hydrogen. If you're trying to do that, at some point you will also reach a regime where it's even harder. So another thing that I'm exploring now with a third PhD student with Joris is to see how good do we actually connect the structure and the envelope. So this is the stellar atmosphere talk, but at some point it's actually not trivial anymore to discuss where to set your lower boundary. And this is in particular interesting for so-called very massive stars, which are stars that have an initial mass of more than 100 solar masses, because there you can have a super Eddington layer that might not launch immediately your wind, but is also still doing something that's not accounted for in the typical stellar structure models. So here we're trying to go deeper in the atmosphere models until we truly reach a hydrostatic regime, and then try to see how we can systematically identify what to do there. Now, in the final minutes, I know I'm already stretching time a bit. We are going to multi-D calculations. So all of the atmosphere models that I've presented you here are actually multi-D models, are actually 1D models, sorry. So what about multi-D effects? The group by Jon Sundqvist in Leuven is actually doing some pioneering efforts on that, and they calculate 2D and 3D models. And what we can do is we can compare what they find with our 1D models, because we're already doing a lot of things in detail in the 1D models, which is why they're numerically costly. So you couldn't simply extend this to multi-D, which is why multi-D models, on the other hand, have to do other simplifications. For example, in the radiative transfer, they just use flux-limited diffusion. At the moment, they also just use LTE population numbers. And so what we can do is we can compare their treatments, and that's what my postdoc Gemma Gonzalez-Tora is working on, and using averages in the density or in the temperature of the 2D and 3D models, and calculating 1D models that approximate this. And so for the O-stars, which is a paper that's already submitted, and we had a first referee report and now waiting for a second one, we are using approximate treatments by introducing a turbulent pressure, something that we already had this idea from the XUDU paper, for example. And we saw that you need this, we see that you need this turbulent pressure to explain the multi-D structure. So that's nicely aligning between what we get from the observation end and from the theory end. And we see that turbulence is something that we can no longer neglect as a factor for setting the scale height in the hydrostatic layers. We're also working on that in the context of Wolf-Rayet stars, where we have the dynamically consistent models. And here we can see that indeed, with the 1D dynamically consistent model, we are able to capture reasonably well the features that we also see in the 3D spectrum. For example, if the velocity does a certain plateau-like structure, we also get this in the 1D, not necessarily to the same strength. That's something to discuss and work on, but in principle we can really mimic the features from the 3D models in the 1D hydro models, which is quite promising because it means that we can really use the 1D models to trace a larger parameter space, which we couldn't do with 3D. Due to time reasons, I will skip over the radiative-driven turbulence. Feel free to ask me more about that. There are also significant challenges to the 1D structure. So what we do at the moment with the 1D codes is nice, but we also know that there are remaining construction sites which will require us to rethink on what we do in our current hot star atmosphere models. The one thing is that the winds are not homogeneous but clumped. The standard treatment that we're doing is an overdense clumps, but this overdensity that we typically approximate is not really aligning with what, for example, here time-dependent LDI models are showing us, or also 3D models are showing us. So there are things how we have to, there are good reasons on why we have to rethink the current code structure that we are using, but that's a longer story. So to wrap up, stellar atmospheres are really a fundamental astrophysical tool, and even for hot massive stars, I think you couldn't do proper research on these objects without them. Here is a picture that we took a while ago with my group, trying to address the different questions. As you see, I have not showed all of the stuff that we are doing, but in principle, we are doing spectral analysis, atmosphere development, we are connecting that to wind theory. We are giving predictions for stellar feedback. We are trying to work towards helping with stellar libraries. We even had a master project now on population 3 stars. We are trying to better couple the structure and the atmosphere models, and we can provide suitable stuff that then can put, for example, into MHD simulations that try to account for the winds of massive stars. And with this, I would thank you very much for listening, and I'm very happy to take your questions.
Thank you so much. Yes. Really nice, very broad picture of all the ongoing work on hot stars in your group. Time for questions. you can raise your hand or open your microphone and ask directly. There is that many of us.
Yeah, good. Then I guess I'm the first. I'm Joe Puls here questioning. So thanks, Andreas, for this very nice overview. I just wanted to make 3 very quick comments. The first comment refers to your statement that it seems that Cygnus X1 has not been analyzed in the past. That's actually not completely true. Artemio Herrero has worked on this object already in 1995, and the group by Sergio Simon Diaz also has worked on this object. So maybe you have a look into this work.
I know that it's been worked on. My statement was indeed a bit short. I meant like analyzed with the code over the last 10 years or so.
Okay, yeah, but even this has been done, I think, by Gonzalo Holgado.
It was in his sample. Okay, that's
right.
good to know. Thanks.
Yeah, because we always use only the optical counterpart 226-868, and then don't mention actually or seldomly mention that this is Cygnus X1. So that was number one. Right. Number 2, I think this is a more important comment, namely you told us or the community quite much about a lot of advantages when you solve the radiative transfer in the co-moving frame. All this is true, but you forgot, or you did not mention one big disadvantage, which also should be clarified, namely that if you don't do a very numerical complicated setup, then the co-moving frame transfer only allows to consider monotonic velocity fields. And that's a big problem because, as you have told us here, these winds are structured and certainly non-monotonic. And in this case, then one has to go to some approximate radiative transfer. This is a big problem in our community. And finally, as you said in your last slides, this turbulent pressure approach is certainly quite useful, or will turn out to have some reality in it. But of course, one has also to compare to observations. Namely, if one is looking into the results, particularly by John Sundquist and others, they find typical turbulence velocities in the line-forming region on the order of a couple of 10 kilometers per second, so say 30, 40, 50 or so. But there are a couple of stars which are more or less not rotating, at least not the projected rotation is quite slow. And then one sees the inner cores. One can really resolve the line cores, and there nothing is seen of such a high turbulence. So there's something more, I guess, than only the turbulent pressure. That was it. But thanks a lot for your nice talk.
Yeah, you're absolutely right. Turbulence is not helping to answer all the problems that we have. It's one ingredient. It's most likely important closer to the Eddington limit.
Yeah.
And for it will not solve the bulk for like an 008 dwarf or something. Yeah, that's very clear. Thank you.
Victor Kalak.
Thank you. Hi, Victor Halak, Université de Moncton, Canada, and Andreas. Big, deep thanks for both Friday stars. I enjoyed them very much because it was my use when I started to work with them. But right now, I'm mostly working with chemically peculiar stars. Yeah, thank you. So we have I have a small question because last model with MESA has shown that because you have radiate your atmosphere quite deep to the star, you can have abundance vertical stratification that will change completely your radiative transfer because your opacity will change. Plus, because depending on the mass loss, you will again add to that abundance stratification because you're losing mass, you're losing elements, atoms at the surface. It's pushed out by the radiative pressure. So my question is, does your code take into account this during the simulation? Because it can change your opacity profile, that final opacity profile that you showed us.
That's a very good point. No, it doesn't. What is assumed here is indeed that you have one fixed chemical composition. Including that is not trivial, and at least in the typical stars that we are looking at, this is not known to be an issue. I know that there are regimes where this can become important. But indeed, it's something that's not included in the current version. There are a lot of potential construction sites, but yeah, we can only try to tackle them one by one.
Thank you. So I just can tell you that because they introduced this possibility for MESA just like this year in spring, so you can introduce opacities in MESA, and you can see how there will be changed like abundance stratification in stellar atmosphere. So we did this for AGMN stars. So those are not like massive stars in your point of view. It's like more intermediate, because we're talking about 3 solar masses, but we do see those effects in AGMN stars. In this respect, have you tried to model chemically peculiar hot stars like AGMN?
This is a temperature regime of
12 to like 2025, 12 kilokelvin, 2025 kilokelvin temperature.
Oh, okay. So this is on the cooler end of what we in principle could do, but we haven't worked on in that mass regime for this kind of stars yet. Okay. But it's very interesting to know. I will take a look into this.
Thank you very much. Thank you.
Yeah, regarding chemically peculiar stars, it's again Joe Pulse. Doesn't one need then also to implement magnetic fields?
Yes.
In AGMN stars, it's known that there is no like strong global magnetic field for AGMN stars observed. Yes, I do know some people claim that they have found weak magnetic field existing, but there is no like confirmation with other researchers in this area. So for now, we assume nothing. If there is magnetic field, we can do spectropolarimetry with Stokes I and V and get some signature, but might be if it's global, but maybe if it's local field, we probably will not see it, like in solar type stars, but like just research. What can we do? We can measure if there is nothing, so it's nothing. Thank you.
Excellent. Any final comment? You mentioned, Andreas, that there are now 3D, multi-D models that take into account the hydrodynamics, but they pay the price of having to assume LTE. And at the beginning, you also mentioned that LTE was not correct, right? That the changes in the structure because of non-LTE effects are just too large. So are these models really a progress, or just allow us to evaluate some of these effects, but in reality they will not be more realistic than the 1D non-LTE models?
That's a good question. So they are a major improvement structure-wise. So at the moment, you cannot use these models to get spectra, to do spectra analysis. This is like a long-term goal, but at the moment, this is not really possible in the way that you use a bunch of lines and you predict all of the stuff and so on and so forth. But what we can learn from this is essentially the open questions that we have in the 1D models and that we cannot solve in the 1D models about the wind structure. So our winds are not smooth. So we want to really understand how does the structure in the wind start. There has been the traditional LDI model that predicts that this is due to that this is happening basically in the outer wind, or not outer wind, but a bit away from the stellar surface. You can relax this to some degree, but also what these models, for example, has shown us, in particular what I just discussed also with Joe in terms of turbulence, is that some structure formation happens deeper. Yeah, so these models really give us insights into that. And then regarding LTE, yes, this is indeed something that is not ideal, but there are ways to do like an approximate non-LTE, which is one of the steps that this group is now working towards. And the other point is for the Wolf-Rayets that have deep launching, you can actually see in our models that at the point of launching, you are still having LTE because it's so highly optically thick that you are almost at the diffusion approximation limit. So you can use LTE in the inner part, and then in the outer part, at some point, LTE will break down. And so for the onset of these winds, these models are really, really helpful. And in order also to confirm that what we find in the 1Ds there are good, and then we would need to have improved models to really learn something about what happens in the outer wind as well. But I'm fully convinced that these models are helping us a lot. They will not replace the 1D models. They're really like a complement at the moment to tackle things from a different angle.
Yeah, maybe we should make here some advertisement. In 2 days, there will be a talk by the author of these slides. Maybe Andreas, you tell.
Yeah, so actually we have from the Massive Star G2 Commission, a regular seminar series. And this Thursday at 2 p.m. European Central Time, we have a talk by exactly Nicolas Moons, who is the author of these plots, and who will give a detailed talk about his work on doing these multi-D models. So if you're interested in that, please join on Thursday. I hope to not have hijacked your seminar now.
Not a problem. Thanks very much for actually passing on information along. So I don't see further questions here. So I think we come to an end, and thank you very much, Andreas, for this excellent talk. Thank you everyone for joining.
Thank you for the invitation, and it was really nice to be here.
Thanks.
See you next time.
Great.
Ciao.
Okay, goodbye. Have a nice evening.
Ciao, ciao.
Stop there.